Yeah, thank you, Stuart. Yeah, I was asked to give a presentation on as the start of this Magnetic Society meeting on sensors. And within this presentation, I will give first an overview on the use and applications of magnetic sensors, and then point to some specific problems which led to the formation of a European project on metrology explicitly for magnetic sensors. And this program, or this project, is called MetMags Metrology for Magnetic Sensors, and I'm the coordinator. So here's the outline of my talk. First of all, I will give, as I said already, an overview on magnetic sensors, on applications, different applications of magnetic sensors, on ranges, and then I also tell you that magnetic sensors are a big market. I will shortly introduce the challenges which magnetic sensors are changing, or some of the challenges at least, and then I try to explain you how the MetMags project is trying to address these challenges. I will tell you about the consortium, the objectives, and the work packages in a bit more detail. And in the end, I give an outlook and I invite you for collaboration and participation in this network. So let us start with an overview on magnetic sensors. One of the oldest applications of magnetic sensors dating back to Gauss times is geophysics, so observation and measurement of the Earth field. There are about 120 observatories worldwide. There are different kinds of sensors used, flux gate, but also proton magnetometers or optical magnetometers nowadays. And with this, you can study the Earth field dynamics, field variations, but you can also use sensors for geological explorations to find minerals, for instance. And later today, we will hear a talk of Lonsdale on Earth, on geophysical applications, and another one by Marsilia on flux gate sensors. Then another application is in space. So also in many space missions, magnetometers are on board, or most of the missions. And for instance, magnetic fields in the solar system or magnetic anomalies of planets are detected there. And also in a later talk by Griffin, there will be more details on this application. Then another important field is healthcare, for instance. So you can use magnetic sensors for magnetic imaging of tissues or in the human body in vivo. And for instance, one important application is magnetoencephalography or magnetocardiography to detect the heart and the magnetic fields coming from the heart. And for this, generally, squid detectors are used, and you require magnetically shielded rooms to detect the very, very small signals in these applications. And another driver, or another field of applications of magnetic sensors is the automotive industry. So in today's cars, if you buy a car, there is, say, 5 to 10 magnetic sensors in each car, and the projection is that these numbers will increase significantly in the next years. And there are different, the main type of sensors which are used for these applications are Hall sensors, which you can use for precision detection, for electrical motor control, and for index counting. And then you have anisotropic magnetoresistance, or in short, AMR sensors, which you use for ABS, braking systems, vehicle stability control, transmissions, and speed sensing. And like also in space applications, you have very strong requirements on the robustness of these devices, on the reliability, of course. You would not want the ABS sensor to stop working just for whatever reason. And you need good signal to noise, wide temperature range, etc. Another very important field which we are all using is magnetic storage. Of course, in every hard disk you have a magnetic sensor to read out the bits. There's a more recent application which is called the MRAM, the Magnetic Random Access Memory, where you have one magnetic bit using a TMR cell, tunneling magnetoresistance cell, in every bit of the cell. And maybe in the future there were more modern concepts based on domain wall storage, where you, like in this proposal, which is from the IBM group of Stuart Parkin, where you have a magnetic wire and a nanowire of, say, 20 nanometers diameter or so, and you have the magnetization into the magnetic information stored in those tiny bits, which are just separated regions here, separated by magnetic domain walls, and you can push those domain walls through this wire, like in a shift register, and read it out using a spin valve sensor or a spin-dependent tunneling sensor. This is, of course, just a concept, but this is a very large market, and every one of us is using this. The sensors which are used there are spintronic sensors, and the main increase of storage density of magnetic hard disks came after the invention of the giant magnetoresistance, for which the Nobel Prize was awarded a couple of years ago. And then later, tunneling magnetoresistance readout sensors were developed. And yeah, the spin torque is one effect which plays a big role on this. So these spintronic sensors are now based, but it's metallic spintronics. Some people also call it magnetoelectronics sensors. And the requirements in this case are very small sensing area, so nanometer scale integration. So the magnetic bits have a bit width of a few nanometers, say 10 nanometers or so. And so you have to be able to read this out locally, and the bit rates are getting up very fast, so you need gigahertz bandwidth operation. So if you look now on the different sensor applications and sensor ranges, there's one diagram which is going back to Pavel Rybka, who is in the audience here. And you can see that for some applications you need very slow and long measurement times, like in geophysical or magnetic anomaly detection. For others, like bio applications here, you need a higher sensitivity, frequencies of 1 hertz or so. And for hard disk drives, now the frequencies are much, much faster than shown here on this graph. And for industrial applications, generally it's sufficient to detect quite large fields reliably, for instance, to sense the position of a gear or so, or a transmission. Let me now come to the sensor market, and I use data from two market studies from iSupply and Frost and Sullivan, which were published 2 years ago. So all the real numbers are from 2009, and all the newer numbers are projections. Well, they did not, of course, take into account the economic crisis, but the order of magnitude is correct. Yeah, still now. So you have a global market of silicon sensor ICs with magnetic sensors of about $1 billion. Okay? And this corresponds to 5 billion magnetic sensors and IC switches sold and shipped. And the drivers for this are the automotive industry, switches, like if you open up your fridge, there's a Hall switch inside, and the light goes on, that's why. And then industrial machines, consumer electronics, and modern applications are now electronic compasses in the smartphone, which are based on AMR sensors. In these market studies, the main sensor ICs are Hall effect sensors, and they can be very cheap, and some of them at least, for low-tech applications, you don't need high specs on that. So you have 70% of the market on this one, and the rest, about 30, on this magnetoresistive sensors, AMR, or more recently also GMR, and for health applications, for instance, squid sensors, and for special applications. But this is a very low number compared to the numbers shipped here. And if you take into account the end users, you have automotive, communications, consumer electronics, aerospace, medical, industrial, and others like non-destructive sensing. Please note that in these studies, also hard disk drives were not taken into account. So of course the numbers of hard disk drives chipped and the readout sensors is also very large. Now, is Europe active in this field? It's one of the questions. And if you want to do a European project, you have to address also the needs of European industry. And you can say, yes, the European industry is well in front, or very well present in this market. So for instance, in the AMR market, there are 3 major players. One is NXP Semiconductors, which is in the Netherlands, which used to be Philips. Then there's Sensitech, smaller one, and the larger one from the US, which is Honeywell. And if you think of GMR sensors, Infineon is the #1 in the world, then the US company NVE, Non-Volatile Electronics, and then again Sensitech from Mainz in Germany. And also the head fabrications, the readout head fabrications, and one of the largest head factories in the world is situated in Ireland. Oh no, in Northern Ireland, so in the UK. Okay, this was the overview over the sensor market and sensor applications, and I now would like to present you the challenges which the sensors are facing. So one, of course, and this one is directly related to the work of the national metrology institutes like NPL, PTB, INRIM, etc., is that if you have a sensor with a high resolution, you need, and you want to measure precisely and traceably, you need a good calibration facilities. So, and there, the national metrology institutes are called to bring such and develop such facilities. Then there are problems due to downscaling of sensor ICs. So why do you do downscaling? Because you want to put more sensors on one wafer so you can make it cheaper. If you have AMR sensors and they are really large, like a few hundred micron wide wires where you get your signal from, then you can basically forget about the edges. The signal from the edges is very small, but if you scale the whole thing down, then the influence of the edges can become very influential and very important. And this can lead to changes of the signal to noise ratio in such sensors, for instance. Furthermore, if you really scale down to the nanometer size, like in readout heads of hard disks, then effects like the spin torque play a very important role. And furthermore, spin torques can also be important for MRAM applications, where you can use the spin torque, and I'll explain this later on what this is, can be used to switch the magnetization or to program a memory cell. And also for sensor development, many questions are open. For instance, you use normally micromagnetic modeling to develop thin film sensor geometries, and you need to know how reliable this modeling is. And it would be good to have fast characterization of materials and parameters. And also new device concepts need new metrology to underpin the developments. And this is why the European Metrology Research Program called a project on metrology for advanced industrial magnetics in its industry call 2010. And based on this, a JRP on magnetic sensors was formed. Just a few words on the European Metrology Research Project or program. It's a large-scale program worth about 160 million euro, which is co-funded by the European Union, one half by the European Union and the other half by the EMRP participating countries. And this is a project and a program focus on metrology. So the main funding or the main project partners are the Metrology Institutes of Europe. And there are different focus calls which are in agreement with the FP7 of the European Union, like health, industry, environment, and some more specific calls related to metrology. So in this call, on a call for advanced industrial magnetics, the following objectives had to be addressed. So first, to develop metrology tools and methods for industrial magnetic sensor development, to develop inline tools and methods for sensor production and quality control, and to develop metrology for testing and calibration. And our project, the MetMags project, tries to address these objectives, and it is done in a 3-year project. The project is running now for half a year, and the total budget is about 2.7 million euro. Let me now introduce the consortium. The consortium consists of 5 partners from the National Metrology Institutes of PTB, and I'm coordinating this from Germany, then the Czech Metrology Institute, CMI, the INREM from Italy, the NPL from here, of course, and UME TÜBİTAK from Turkey. There's one industrial partner. There's the opportunity to have, at that time it was one external partner involved using a so-called Researcher Excellence Grant, and this is done at Hitachi in Cambridge in the research lab there. And then we have several collaborators like NXP, providing sensor samples, Seagate, Bartington, RAL, and Czech Technical University, to name just a few. Okay, the structure of the work package is the following. So we have one work package on metrology for AMR sensors, one on testing and calibration infrastructure, one metrology for spin torque materials and devices, one on micromagnetic numerical modeling, and one on metrology for advanced magnetic sensor concepts, new concepts for magnetic sensors, and the Researcher Excellence Grant also related to this field. And they are specifically on spin-dependent Hall effects. And then, of course, we've got some more non-scientific work packages, which are nevertheless very important, especially for the reporting. Okay, let me now explain to you in very short time the different work packages. So the first one addresses metrology for AMR sensors. And I have already told you about one of the drivers for this. You have the downscaling of AMR sensors. And this is a sketch of a kind of sensor geometry. So you have these RMA sensors, AMR sensors, in a bridge configuration. And these lines here, these are the magnetic elements. And then the currents run through it in a meander shape. Okay, and there, as I said, if you have 100 micron wide wires and 1 millimeter long, then you don't worry about the edges. But if you scale them down, the edges can play a role. And if you scale down to a micron range or so, even individual defects can play a role. Okay? And these material defects and these edges, we want to investigate. And another problem is, or can be, strain. So if you package your sensor, or if you have your sensor working in different thermal temperature ranges, then there can be thermal stress and strain. And in the ideal case, the sensor's material is permalloy, so there's no magnetostriction. But if the alloy is not perfect, then there might be magnetostriction, and then the sensor signal might change due to that. Okay? And so what we would like to do, or what we are doing in this project now, is to develop metrology to address those 2 points. So for the first one, we will study real magnetic sensors coming from our collaborators, NXP, small downscaled sensors, study the magnetization states at the edges and at individual defects using high resolution imaging by Kerr optics and by MFM, and compare this to magnetotransport measurements. So do we see any degradation if we have one single defect or more? And then in a second project, we will develop a strain tester to study the effect of strain and stress on the magnetic performance, on the electrical performance of the sensors. And we would also like to combine this with imaging in an AFM. So we can see whether local defects of composition may play a role there. The second work package is on sensor calibration and noise measurements. And there, as I said already, if you got really good sensors, you need even better calibration facilities. And there are two of those facilities which are shown here. So this is a facility for earth field compensation at NPL. And this is one facility at PTB Berlin. So this is a magnetically shielded room. The outer side is like, how much is this? 15 times 15 times 15 meter. And the inner shielded cell is, I think, 2 meters cube, and all around there's magnetic shielding and compensation, but which you can imagine is this was very expensive to build, and you needed a lot of soft magnetic shielding. But for this, you have the most quiet, electrically quiet room in the world in this building in Berlin. So, and such facilities with very low magnetic noise you need for high quality calibrations. And industrial needs in this field are now something like operational temperature calibration. So if you use your sensors at different temperatures in space or for cars or whatever, how do they degrade? Are they still working properly? We want to provide low magnetic noise environments. And then other problems are multi-axial sensor calibration. So 3 axial sensors should be calibrated with a very high angular resolution. And we want to define well-defined measurement calibration procedures for the stakeholders. Yeah, once again, these points. So calibration at operational temperatures in a range preliminarily minus 40 to 100, but this depends on your input also in the last session. Noise measurements below 1 nanotesla at square root hertz and lower than that. Calibration of 3 axial magnetometers with 0.05 degree uncertainty, and to provide a best practice guide for magnetic field measurements and sensor calibrations. And there will be a talk on this at my call later on. Okay, the third one is on inductive metrology for spin torque materials. And I have promised you already, I wanted to introduce you to the effect of spin torque. So imagine you have a nanostructure which is very narrow, and you run a current through this, and this is magnetic. So there's a magnetic layer, a non-magnetic spacer, and another magnetic layer. And if you run a current through this, then the electrons will be spin polarized. And when the magnetization of the second layer is not collinear, the magnetic moment of the electron will be transferred to the magnetization. And if you have sufficiently high current densities, then this can be sufficient to switch the magnetization of the second layer. Okay? And this is applied for spin torque MRAM. So you can have such a cell, you run a current like this, then you switch into a parallel state, and you run the current the opposite way, you switch to the anti-parallel state, and you can read it out by TMR effect. And there are many prototypes of these devices now developed by Samsung, for instance. You can also have spin torque precession, spin torque noise and sensors, etc. And usually if you have such materials and you want to use them for applications, you need to determine the critical parameters. And one of the most important critical parameters is this critical current density for the start of spin torque precession. And what you usually have to do is to make a nanostructure which is patterned down to, say, 100 nanometers diameter, and then run a current through it and measure. And this, of course, takes a lot of time because you have to pattern the whole thing and make lithography, which is very costly and time-consuming. And we are proposing to do just inductive measurements of those samples, like TMR samples, use inductive detection, and from the inductive detection we can learn something about the dynamics, and the dynamics, the damping or the FMR line widths are directly related to the critical current density, and so we can try to derive it from that. So to have a faster inline testing tool for spin torque materials at the end of this work package. And there will be talk by Massimo Pasquale later on this subject. The next work package addresses micromagnetic numerical modeling. So if you develop new read heads, for instance, for a hard disk, then there will always be magnetic modeling be done beforehand. And one of the most important parts is to learn about the magnetic domain configuration in such nanomagnetic thin film elements or multilayer elements. And the devices which are simulated are AMR, GMR, TMR, and spin torque sensors on the micro and nano scale. And there you have a lot of micromagnetic codes. There are public codes. There are codes which you have to buy and which are very expensive or can be very expensive. And you can compare them, and sometimes they deliver the same result and sometimes not. So the question is then, of course, which result is correct? And this problem should be addressed within this work package. So as a first step, new and relevant standard problems for the validation of codes should be derived. So you develop a problem, then you have many different codes trying to solve this problem, then you can compare it. And in the ideal case, you can compare it also to some measurements on these devices to validate it. So based on these standard problems, you will have a validation tool for different micromagnetics codes, and at the end you can use this for the optimization of your codes, for instance, with respect to computation time. And so we hope that after this, at the end of this JRP, we'll have also more reliable and optimized micromagnetic numerical modeling tools for the industry and the research. And there will be talk on that by Alessandra Manza later on. And the last work package will be described in the following. So there are new and more advanced sensor concepts, like you can use semiconductor Hall sensors on the nanoscale for magnetic bead detection, for instance. And they will be studied here within this work package. You can use now graphene to fabricate nanoscale Hall sensors, or you can use nanowire domain sensors. And also semiconductor spintronic sensors may play a very important role in the future. And all those should be studied within the work package 5 and the associated reg. So the aim is to develop first setups for the characterization of such advanced sensor concepts, like to study the sensitivity of those micro-patterned Hall sensors at different temperatures, for instance, to study magnetic domain configurations in those magnetic nanowires, which can be used as domain wall sensors. And this is, of course, supported by micromagnetic modeling, for instance, as developed in the work package 4. And there's also the spin Hall sensors investigated at Hitachi. In this case, it's the so-called spin injection Hall effect. So you can have a structure of a two-dimensional electron gas coupled to a two-dimensional Hall gas, and in the middle of the interface between them, you have PN junction, and by applying light to it, you can generate electron-hole pairs. And if the light is polarized, then you can have spin-polarized carriers here and there, and they give rise to a so-called spin injection Hall effect. So the spin-polarized carriers are deflected somehow and give rise to a Hall voltage, which is measured. And this is, at the end, a new type of sensor, a solid-state sensor for the polarization of light. Okay? And so within this work package, electrical metrology of spin currents and dynamics of spin-polarized charge currents in non-magnetic semiconductors will be investigated. You use electrical detection. You can scale down to the nanometer size. It's non-invasive and it works at room temperature. And it might allow in the future very low power spin devices and sensors based on semiconductors. And more details will be given by Elisa De Ranieri in her talk later on. Okay, finally I would like to conclude this part of the talk by showing the structure of the work package. So we have a management work package, and then we have this advanced concept here, the spin torque, which is in exchange with these, and with the modeling, both are supported. The calibration facilities can be used for practically all the sensors under investigation. Then you have the AMR sensors, and for instance, the AMR sensors, the domains are also important in the domain wall devices, which are covered in this work package. And finally, all this should lead to an impact, so we have not only scientific publications in the end, but we would like to support the stakeholders with this European project. Okay, and there I am at the end of my talk. So, the summary is the following. I think you will all agree that advanced magnetic sensors require also advanced metrology facilities and tools. We will try to develop such metrology facilities within the MetMags project for development, for testing, and for calibration of sensors. And please remember, such projects also are for the stakeholders. So you can collaborate directly. If you're interested in some specific parts, you can contact the specific work package leaders and we can discuss collaboration. We need your input for best practice guides, for instance, what is important for you there. And you can also become member of the stakeholder committee and get informed on the further progress of the project. And with this, I would like to thank you for your attention.